And so homework number 1 is about the mixer. So, how this mixer works is that you have a GM stage at the bottom, and you have a switching stage on top, and then the resistive load. So when the LO signal is at 1.6 gigahertz, driving this these M3, M4, M4, and M6 switching stages to fully to one side or the other side with the plus minus 1 gain. That's how it works. And the question is, what is the mixer's conversion gain to 800 megahertz when FRF is 2.4 gigahertz? So how that works is that you have a 2.4 gigahertz mixing with 1.6 gigahertz, and we learned that the output will be sum and difference frequencies. So one of them will be at 800 megahertz. But as you can see on the right at bottom, this square wave switching, which is done by M3 to M6 transistors, gives you the gain of +1 or -1, fully switched to positive direction or fully switched to negative direction. In that case, the fundamental term has 4 over pi, the coefficients here. So if you go to the answer page, this is like you multiply the two signals, which is the first, if the mixer is switched to fully to one side, it's just a simple amplifier, GM times R. Here, I'll ignore the polarity. Okay, let's just look at the magnitude, GMR. And the input signal will be RF signal with some cosine function. And then the fundamental term has a 4 over pi coefficient on top. So if you multiply these two, now you have a product of two cosine terms, cosine omega RF and cosine omega LO term here. So when you multiply these two, it says, output will be sum and difference. So you'll get one at 800 megahertz, the other one at much higher frequency. So they will split into half and half. Therefore, there is another additional factor of 1/2. So if you multiply them up, then you'll get 2 over pi times GM times R. So it's pretty straightforward. The second part of the question is that what is the mixer's conversion gain to 800 megahertz if FRF is 5.6 gigahertz? Now, 5.6 gigahertz component comes to 800 megahertz when RF signal is mixed with the third harmonic of the 800 megahertz. That's the only time it can come down to 800 megahertz. Other terms will go to different frequencies. So in that case, you come to this square wave chart again, figure 2. And if you look at the third harmonic here, there's a 4 over 3 pi term. So it's just a scale version. So this term will be mixed with the 5.6 gigahertz. Therefore, if you go to the second page again, instead of 4 over pi here, you put 2 over 3 pi. I'm sorry, 4 over 3 pi. And then you can, by the same math, when the two cosine waves are multiplied together, you get a 1/2 factor. So the answer becomes 2 over 3 pi times GM times R. So it's rather pretty straightforward. Now, what this means is that we are, in most cases, we are only interested in down converting the signal at F0, not at 3F0, right? These higher frequency components are more of interferers, and we don't want them to come down because of this kind of a harmonic mixing. So what can we do to reduce the conversion gain of this this type of 5.6 gigahertz coming down without affecting the conversion gain of A, which is what we are interested in? Well, what we should do is that if you look at figure 1, there are so many things we can do, but I can only say a few things, okay? what we can do is that we can make this right now. The GM stage is very wideband circuit. It just works for the all frequencies. So we have to make it some sort of a bandpass filter type of function in there. What we can do is either you can degenerate the input stage with the inductor, or that's one way. And another way is you can split the current. Maybe I can use a pen in this case. We can split the current like this instead of using a common, and then we can use some sort of an LC short circuit that resonates at 2.4 gigahertz. So at 2.4 gigahertz, we have a regular, this series LC shorts. So M1 and M2 are just the regular differential pair. But at 5 gigahertz, 5.6 gigahertz, it looks like a short, like this sort of inductor. No, I'm sorry, capacitor. Yeah, it becomes a higher impedance, and then that reduces the gain. And or another thing you can do is you can also do the same trick. You can put it somewhere between A and B, because once you mix it through this by this switching stage, you know, the 5.6 gigahertz already comes down to 800 megahertz. So nothing you can do to remove it. So you have to somehow work in this region to boost up the gain at 2.4 gigahertz, but reduce the gain at 5.6 gigahertz.